Welcome. My name is Maurice Hoogheef. I'm an assistant professor in the section of Flight Performance and Propulsion. In this short video, I want to explain to you some considerations behind novel aircraft design and the ideas that exist to achieve sustainable aviation. When we take a look at the evolution of passenger aircraft of the past 60 years, we have to look rather closely. Most changes are incremental, rather than revolutionary, of course with some major improvements in certain areas. However, the general layout of the aircraft has remained predominantly the same. This so-called tube and wing configuration is well understood, meaning that there are low economical, technical or safety risks involved. The configuration itself is a very efficient compromise between aerodynamics and weight with a pressurized passenger cabin. The cylindrical shape of this cabin is ideal to withstand pressurization, such that the passengers can survive at high altitude. The word compromise is essential in aircraft design, as the design itself must find a balance between conflicting requirements, ideally at the lowest possible cost and highest possible energetic efficiency. This means we are looking for a very safe, low weight, high aerodynamic efficiency design. The evolutions over the past decades have primarily focused around novel materials to reduce the weight and increase the engine efficiency. This is immediately obvious when we look at the graph showing the fuel efficiency of a large number of aircraft introduced over the last decades shown behind me. If you take a look at this curve, you see that this starts flattening out, and making large gains becomes more and more difficult. Moreover, integrating an even larger engine with an existing aircraft becomes more and more challenging. Take a look at the difference in size between the engines on the same aircraft. The modern, much more fuel-efficient version on the left has a much larger diameter. This causes all kinds of integration challenges, such as sufficient landing gear height for clearance, or drag due to the larger engine itself. As such, there is a limit to integrating ever larger engines on existing aircraft. Before we look at novel aircraft design, it is important to take a look at what aspects airplane designers try to improve. Therefore, it is important to understand that the aircraft design process is cyclic in nature. It is often referred to as the aircraft design snowball effect. And similar to a snowball rolling down slope, any increase in aircraft mass requires more lift to carry that additional mass. Lift itself doesn't come for free, and lift causes more drag, which must be overcome by larger, more powerful engines, which in turn require more mass again. Unlike a snowball, this process generally converges and we can end up with a design that can meet our requirements. But this effect illustrates that there is no free lunch and generally always a compromise between different requirements or disciplines. Luckily, the process also works the other way around, providing us with a number of areas that we can look to improve. Airplane designers often try to look at improvements in the so-called payload range efficiency, or in other words, the ability to transport as much payload over the longest distance with the least amount of required energy or fuel as possible. The range that an aircraft can fly with a given amount of energy depends on its design. This design can be expressed as the product of the aerodynamic, propulsion system and structural design. All of these are in fact key elements of the aircraft design snowball effect. Now that we know this, let's take a look at some novel aircraft designs and try to understand some of the ideas and challenges behind these concepts. Flying V, which is covered in much more detail in the next lecture, offers a significant mass reduction compared to conventional tube and wing designs, hence lowering the energy use. The strut-braced wing shown here features a very high aspect ratio wing, similar to a glider aircraft, which is structurally supported with an additional strut. The aim of this design is to reduce the drag during cruise, while trying to keep the weight as low as possible. Another concept aimed at reducing drag is the tip-mounted propulsion layout, shown here. This actually also flies at a lower speed, allowing for a lighter wing, because the wing is not swept backwards, and it features very efficient propeller engines. Necessarily distributing extra engines should not lead to a weight increase, which can be very challenging to deal with. Additionally, all these configurations that I've just shown can be combined by designers with different energy sources in an effort to achieve beneficial synergies. For example, distributed propulsion can be enabled by electric motors that can be more easily placed around the aircraft. In this particular layout shown here, the aim is to increase the lift during low-speed operation of the aircraft, which can be very beneficial for operating from a shorter runway, hence requiring less complex, thus lighter flaps for takeoff and landing. The propulsive empennage concept shown below is aimed at exploiting a potential synergy between thrust generation and the vertical and horizontal tail that are needed to control and stabilize the aircraft. Of course, none of these benefits come for free, and the changes may often result in additional mass, compromising the design. Therefore, we must always keep all the aspects of the snowball effect in mind. Another, less conventional aircraft is the blended wing body, targeting an increase in efficiency to create lift at a lower drag cost. However, a challenge with this design is the limited design experience and the larger uncertainty that we have in, for example, estimating its structural mass or estimating its aerodynamic efficiency. Similarly, the box wing or Prandtl plane that is shown here aims to reduce the drag and cruise, but it also is impacted by the limited design experience. The traditional tube and wing layout is very well understood thanks to years of design, manufacturing, and operating experience. Hence, we should always consider many more aspects when discussing novel aircraft layouts or designs. Once we have come up with a design, we should also consider the challenges in actually manufacturing it, certifying the design process to ensure safety, and integrate the aircraft with existing airport infrastructure to allow smooth operation. These aspects, together with the design itself, form topics for much more research.